uh, between Albert Einstein and Neil Bohr. And it was a debate of reason. It was a debate of theories. It was a debate of predictions. And this debate was not it was not only physical in nature. This debate was not an open debate all the time. This debate was an interaction through writings of the Nobel scientists, and this debate was a kind of interaction between the two schools of thoughts that developed when there was advent of quantum mechanics. So, in this video, I'll be talking about this debate. I'll give some brief description of this debate. So, to move on, I mean, the Bohr-Einstein debate. I mean, it remains a moment in the history of physics, show causing a kind of tension between deterministic uh, and 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 a deterministic view of world view of classical physics and the probabilistic or we can call it indeterministic nature of quantum mechanics. The legacy of the debate extends beyond physics, impacting our broader understanding of the nature of reality and the limits of human knowledge. So, uh, the Bohr-Einstein debate it focuses into the heart of quantum mechanics, exploring the profound implications of theory on our understanding of physical reality. And I mean, at the core of Einstein's skepticism was a commitment to the determinism inherent, which is basically an inherent property of classical physics. A worldview, I mean, he found it difficult to reconcile with the probabilistic nature of quantum phenomena. The famous EPR paradox, which was formulated by Einstein, Podolsky, and Rosen in 1935, it challenged the completeness of quantum theory by highlighting what they perceived as a lack of local realism. And Einstein's discomfort with the apparent indeterminacy of the quantum mechanics was encapsulated in his famous quote. In his famous quote, what he quoted was that God does not play dice with the universe. On the other hand, Neil Bohr embraced the probabilistic nature of quantum mechanics, arguing that attempts to attribute classical properties simultaneously to quantum entities were misguided. So Bohr's concept of complementary uh, emphasized the idea that certain quantum properties, such as wave and particle aspects, could not be observed simultaneously. Uh, the well-known Solvay conference became a stage for Bohr and Einstein to present and defend their contrasting views on quantum mechanics and the philosophical implications of its principles. Bohr's response to the EPR paradox emphasized the importance of understanding the limitations of classical concepts when dealing with quantum realm. Complementary, as articulated by Bohr suggested that the very act of measurement influenced the system being observed, challenging the notion of an objective reality. which was thought to be independent of observation. And 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 Werner Heisenberg, I mean, in his uncertainty principle, the well-known Heisenberg's uncertainty principle, a fundamental aspect of the quantum mechanics, it further supported Bohr's argument by introducing the inherent, uh, or I should say, the intrinsic limitation to the precise or the precision of certain kind of measurements. The uncertainty principle asserted that there were fundamental limits to the simultaneous procession with which certain pairs of properties, such as position and momentum, energy and time, angular momentum and angle, could be known. Bohr and Heisenberg's work laid the foundation for a new understanding of the microscopic world, the one that required a departure from classical intuition. The Bohr-Einstein debate influenced generations of physicists, prompting deep reflections on the nature of reality and the role of human observations in shaping it down. So Einstein's insistence, on the other hand, on determinism was in line with his commitment to a clockwork universe where the future could be precisely predicted from known initial conditions. However, the quantum revolution challenged this deterministic worldview, introducing a level of unpredictability that Einstein found philosophically unsettling. And Bohr's insistence on the indeterministic nature of quantum events was grounded in a recognition of the empirical success of quantum mechanics in explaining the experimental results. The concept of wave particle duality, where particles could exhibit both wave-like and particle-like behaviors depending on the experimental context, was central to Bohr's argument. And Bohr's interpretation of quantum mechanics was not without its critics. At the same time, and alternative interpretations such as the many world interpretations emerged over evolving time. The Bohr Einstein debate, it spurred ongoing discussions about the role of philosophy in physics, with questions about the nature of reality extending beyond the confines of laboratory. The philosophical implications of quantum mechanics raised questions about the very nature of existence, challenging our intuitive understanding of the physical world. And Einstein, as a critic of quantum mechanics, his criticism was not solely rooted in philosophical discomfort. He sought to uncover the potential hidden variables that could restore determinism. And However, the well-known Bell's term, proposed by the physicist John Bell in 1964, suggested that certain types of hidden variables were incompatible with the predictions of quantum mechanics. And Bell's experiments, designed to test the predictions of quantum entanglement, later provided empirical support for non local correlation that Einstein had found so objectionable. The debate surrounding quantum mechanics transcended the scientific community, capturing the attention of physic, the attention of the physical realities. I mean, the philosophers and general public stood in line with realizing what actually could be the possible reality of the nature. The Bohr Einstein debate became uh, emblematic of the broader tension between scientific progress and the human desire for a clear, deterministic understanding of the universe. And again, the Bohr's insistence on the limits of classical uh, uh, in, intuition and the necessity of adopting a new conceptual framework marked a paradigm shift uh, in how physicists approached the quantum realm. And quantum mechanics, with its inherent uncertainties and probabilistic outcomes, challenged humanity to accept a reality where a familiar certainties of classical physics no longer held. The Copenhagen interpretations, heavily influenced by Bohr's ideas, became one of the dominant views in quantum mechanics, providing a pragmatic approach to understanding quantum phenomena. And on the other hand, the Einstein's legacy, while enduring the annals of physics, also underscored the challenges of reconciling deeply ingrained philosophical convictions with the evolving nature of scientific understanding. This debate between Bohr and Einstein, rather than providing a definitive resolution, left an open mark, an open mark on the philosophy of science, encouraging continued explorations and reflections. And quantum mechanics, with its wave functions, probabilities, and entanglements, offered a new lens through which to perceive the universe, uh, one that required a departure from classical certainties. The advent of quantum computing, if we look at that, the quantum computing and quantum information science further underscored the practical implications of quantum mechanics, demonstrating its relevance beyond theoretical debates. The Bohr Einstein debate became a touchstone for discussions on the nature of scientific revolutions, highlighting the resistance and skepticism that often accompany a paradigm shift from, from, from one class of thought to another class of thought. So Bohr's insistence on this this module of quantum phenomenon challenged scientists and philosophers to reconsider their preconceptions about the separability of classical concepts. The development of quantum field theory and the Standard Model further solidified the role of quantum mechanics as the cornerstone of modern physics. Quantum entanglement, once a source of controversy, became a key resource in quantum technologies, paving the way for advances in quantum communication and quantum cryptography. Bohr's emphasis on the pragmatic use of quantum mechanics, despite its challenges to classical institutions, resonated with the generation of physicists who valued the predictive power of the theory. The debate that we are talking about, the Bohr-Einstein debate, it prompted reflections on the very nature of scientific inquiry, urging scientists to confront the discomfort that arises when a familiar certainties are falling into the domain of familiar uncertainties. The influence of this debate extended beyond physics. It was not confined to the Department of Physics. It was a basis of inspiring discussions in philosophy departments and among scholars interested in the philosophy of science. The philosophical implication of quantum mechanics explored in the aftermath of Bohr Einstein's debate, raised questions about the nature of observation, reality, and the limits of human knowledge. The legacy of the debate could be seen in the ongoing exploration of the quantum foundation, where researchers sought to uncover the fundamental principles underlying the seemingly mysterious behavior of quantum systems. Quantum decoherence, an area of study emerging from quantum foundation research, sought to explain the transition from quantum to classical behaviors by examining the interaction of quantum systems with their environments. The, the concept of of superposition, once a source of contention, found practical applications in quantum computing, where qubits could exist in multiple states simultaneously at the same state of time, enabling parallel processing. The Bohr Einstein debate, while centered on fundamental questions in physics, resonated broader discussions about the nature of the scientific progress, the acceptance of uncertainty, and the evolution of human understanding. Bohr's emphasis on the quantum phenomenon underscored the need for a flexible approach to understand the quantum realm. And they were certainly challenging the scientists to go for classical prejudices. And this debate highlighted the importance of acknowledging the limitations of language and conceptual framework when grappling with the abstract and intuitive nature of quantum mechanics. The challenges proposed by the Bohr Einstein debate encouraged physicists, and I would like to repeat it again and again. It was a basic argument, it was a basic debate that is still open, and the interactions are still going on in all domains, in all directions. And if we look at interpretations of quantum mechanics giving rise to approaches such as the pilot wave theory and the de Broglie Bohm theory, Bohr's insistence on the observer's role in shaping reality sparked discussions about the nature of consciousness and the interplay between the observer and the observed in the quantum world. The Bohr-Einstein debate, while making a kind of demonstration where we can see some kind of clash between the two state of beautiful minds, uh, it certainly paved a way for an open uh, uh, insistence where one uh, group of people could certainly insist on their view, on their understanding, on their expected experimental demonstrations. So this debate proves to be an open thing. Maybe all the debates that we see in the modern world, uh, the basis of all those debates, based on reason, based on experiments, based on theoretical models, could be could be taken as a stringent uh, uh, tool for any sort of understanding, for any sort of realization. And at the same time, if we talk about the quantum entanglement experiments, such as those conducted by Allen, provided empirical support for non-local correlation that had been a focal point of Einstein's objection. So the Bohr-Einstein debate continued to inspired literature and documentaries, became a cultural touchstone for those interested in intersection of science, philosophy, and the human quest for understanding. Quantum entanglement, I want to lay some more emphasis, once considered a source of controversy, became a key resource in quantum technologies, promising advancements in fields such as quantum communication, quantum teleportation,